All right.
Well, good morning, good afternoon, and good evening. Welcome to Fluorescent Fridays. I think it's appropriate to give all of those greetings since we are global today. We have people like myself who are still yawning from and on the first cup of coffee, and we have other people in China who are just getting ready to turn in for bed, but they're going to take the time to hear this wonderful webinar today. This is Fluorescent Fridays. Before we begin, I should introduce myself. I'm John Seymour, and I'll be your host today. I work as an adjunct professor of color science in Clemson University. Go Tigers. And I work as a consultant under the name John the Math Guy. You may have heard of that before. Let's see here. Before we begin, make sure that your cameras are off and your mics are muted during the presentations. There is a chat box, and I want you to tell us who you are. If you would, add to the chat your name and which university you were from, or which organization if you're not with a university. The Inter-Society Color Council is what is sponsoring this event called Fluorescent Fridays. It's a global platform for university students from all disciplines to network with color professionals and fellow students around the world. If you're interested in getting involved, please check out our website, iscc.org, for more information and to learn about the benefits for becoming a member of the ISCC. It is cheap. So it's not a $1,000 a year thing. I think it's a $25 or something like that. Today's Fluorescent Fridays, I am overjoyed. I think the word is frabjous to be introducing Ronnier Luo. He is certainly a luminary in color science. I looked on Google Scholar and found that he has over 650 papers that he has his name on, which is an unbelievable, just unbelievable. I can't imagine. But a lot of his papers he has co-authored, and the other people involved are students. So I think it's fair to say that Ronnie is responsible for inspiring a great deal of the scholars in color science and a lot of the ongoing research that's in many fields. A lot of what he has to do is about color order systems, color measurement, but he's written papers recently on color harmony, on the measurement of human skin, all kinds of different things. So I am very pleased to bring him in today. Our guests, let's see, he's from the Color and Engineering Lab at the College of Optical Science and Engineering at Zhejiang University in China. Their work is focused on academic research on color science, imaging science, and illumination engineering. Members actively collaborate with leading global companies to develop innovative technologies and are devoted to the development of the national and international standards. And I will turn over the screen to Ronnie.
Right. Thank you. Hello. Thanks very much, John. Right, you give us the very thorough discussions and the introduction, and it's my great pleasure to be involved with the color science. The look back, right, is the 30-40 years. Okay, so today, right, is our team will present a topic, right, on the color science meets the customers. Why we picked this title, right, is color science is very much the applied science. So we use the, color science as a foundation, we developed, right, a range of the technology to serve the industries, and various the products, right, is the, being produced. So we contributed many of this, okay? And we have the 4 presenters today. So let me start, right, is the, what is the scope of the talk today? The first one, I'm going to introduce the basic of color science, right? So then, right, I will, introduce my colleagues and who will give the topics in the field of the color imaging reproductions. So we have the subtopics of the fidelity, color fidelity, and picture risk, and to make the images that looks beautiful. And finally, right, is what are the color scales for imaging, okay? So these are the 4 topics tonight. So the whole program will last for about 1 hour. So look at the color science, right? Is the red part in the middle, right? Is the foundation, and the today's topic, right, will be in the imaging science and the illumination engineers, okay, as the applied, application fields. So firstly, right, is the well, many people that see this, right, is the how we perceive the colors. So firstly, right, we need to have our illumination, okay, is starting from the sun as example here. It shines to an orange, that is an object, and then, right, is being perceived by the our human vision systems, okay? So we must have these 3 components in order to perceive the color. But if it's self-luminance displays, right, we will see on the screen, which is the self-emitted light and perceived by the human eyes. But in this, the field, right, is very much, right, associated with CIE, International, Commission on Illumination, which is the big umbrella, right, is involved in most of the color technologies, okay? So the CIE colorimetry is to serve as the cornerstone of the color science. So if people ask, right, is then what is the CIE colorimetry? I would say, look at it, it's just X, Y, Z. We specify the color and the light in terms of 3 magic numbers, X, Y, Z. Okay. So X, Y, Z, right, correspond to the red, green, and the blue. So it's what we are saying, right, is that we can present each individual components in terms of the mathematical functions, right? So the visible range of the visible spectrum is from 400 to 700 nanometers. Okay, so this is right, is the reflectance representing, right, is this orange. Okay, and then right is the spectral power distribution for the sunlight. This is D65. And then the right is the human vision systems. We have the X bar, Y bar, Z bar. I just give the very simple examples. So you can see the right is for each individual object, we can divide them in terms of the spectral reflectance. So if we multiply this, right, and spectrals, wavelengths by wavelengths, and we make sum of that. So the product sum is X, Y, and Z, okay? To simplify this, right, we can say that we are using the right is the standard, and the lightings, okay? And the standard observer color matching functions, so we can compute X, Y, Z. So it's just like, right, is we are using the red, green, and the blue lights in order to match this orange, okay? So once we have done that, so we can give the numerical specification. We can reproduce the colors and the lights anywhere in the world. Okay, so this is right, is a communicating color and the light by numbers. Okay, so this is right, is the CIE colorimetry. So this is the cornerstone of the color science. So over the years, right, is the CIE, right, is the developed a number of standards. Okay, so this the three in yellow icons, right? They are the most important, right? One is XYZ, as explained before. Any color can be specified in terms of the right is the three numbers XYZ. However, right, XYZ is not a uniform color space, right? So then, right, we have the uniform color space UCS, and nowadays, right, we have color appearance models. The XYZ, right, is the serve as the color communication tool. UCS, right, to give you a uniform color surface to do the color difference, evaluations. Okay, the color appearance model, it allows us, right, to transfer colors in the different viewing environment. Okay, so this is right, is the the three sets of the important platform as being widely used in industries. Okay, so all this, right, is the small, the gray and the blue parts, right? They are the components belong to each of the individual categories. So how we apply this, right, in industry? So we have different types of the color reproductions. So in industry, right, is when we have two colors. Let's say, right, is I have XYZ1, XYZ2. If these the two colors match, then it means, right, is the XYZ equal to each other, for example. So they produce the right is the A color match, right? So if you want to produce, right, a mobile phone with large numbers, you want to control the color accurately. So then, right, you need to control the different phones with the XYZ equal to each other, right? So we have different types of color reproduction, right, as introduced by the Professor Bob Hung, okay? And so we have the right is divided them into the two categories. One is we call the color fidelity. Another one is color preference, right? Color fidelity, right, is it's saying every color, let's say a cloth, is you have the reflectance numbers. You have to reproduce, right, to match is the reflectance 31 numbers, right? Is the from 400 to 700 nanometers, right? So this is what we call the right is the spectral color reproduction. Colorimetric in the XYZ, right, is the so let's say, right, is we have the mobile phone colors red, XYZ. We have closed colors, surface colors, that is XYZ. When they match under the fixed conditions, then this is we call colorimetric match. I apologize for this. And then, right, we have the appearance. So we call it JCH, let's say lightness, chroma, and hue. So you look at the same image, right, on the mobile phone in the morning, you want to reproduce the same appearance at night, the image needs to be changed. So how can we do that? So this is what we call the appearance match. So there, LCH, right? So lightness, chroma, and hue, the perceived, and tends to be matched in all different conditions. So this is right. Top three is fidelity. The bottom one we call the preferred color reproduction. No matter how accurate the reproduction is, but normally we don't like it. We want our prefer our skin colors to become paler, to become right is the deeper shades, right? So this is right is we need a preferred color reproductions. Okay, so my colleagues will introduce this right in the following topics. The example given right will be, so we have done a lot of work in the mobile phone these days, right? Is the we have the what we call the right is the for perfect mobile phone, we needed to achieve the three goals. One is fidelity, so the images captured by the mobile phone and the real scene need to be really accurately reproduced. This is what we call fidelity. And then, even though they are very accurate, they can be truthfully reproduced. It's not what you want. You want the picturesque to make it look beautiful, okay? And finally, right, is well-being. So we needed to look after, right, is the all different age groups. When they look at the images in all different conditions, we needed them to look at this, and visual comfort and not suffering the circadian, variations, okay? So well-being will not be introduced. I finished my sections, okay? Now, right, is the, my colleague, right, is the Fiona Fan, and she will give the talk, in fidelity, okay? John, can you introduce the Fiona, please?
Certainly. Fiona Fan received her Bachelor of Science degree in Optical Engineering from Nankai University. Currently, she's a PhD student supervised by Professor Ming Luo at Zhejiang University. Her research work is focused on camera calibration and multispectral imaging. Interesting. Fiona will introduce the technology for camera devices designed to achieve what Ronnie had referred to as fidelity.
Fiona, please.
Thanks for your introduction. Hello, everyone. Today, my topic is about color fidelity and spectral imaging. First, I will briefly introduce the spectrum tunable LED lightings. A spectrum tunable LED system contains multiple LED channels. The left figure shows the spectral power distribution, SPDs, of each LED channel, with a total number of 18 channels. This system can easily and accurately simulate any lighting environment having different spectral power distributions. This LED system can be applied in lighting research, health lighting, medical lighting, color rendering, and sensor calibration, etc. For example, it can serve as a daylight simulator.
Wow, just one moment, right? It's right. I needed to go out again. Sorry, right? It's the Fiona. Just wait for me. Just one
Can
minute.
I share the screen by myself?
And just one minute, right? It is here. I think so. Oh, I've done everything, right? It's just one moment, right? It's I think it's this one. Hey, apologize for this, right? It's right, it's here. Sorry. Yeah, Fiona, please.
But I cannot see the screen right now.
It's coming now. Okay, you don't see that? Okay, sorry. It should be, but
I think you just need to make it full screen now, Ronnie. It's showing.
is it okay?
Yes, it's okay now.
Okay, apologize for that. Okay. Please.
Okay. Next, I will introduce some basic concepts in digital camera imaging. The camera imaging process is quite similar to that of the human visual system It follows a linear model and is determined by 3 factors, including the SPD of illuminant, spectral reflectance of object, and the spectral sensitivities of the sensor. The sensor response is the integration of the product of these 3 functions. If the sensor sensitivity is the color matching functions of human eyes, we can get the CIE fast stimulus values XYZ. If the sensor sensitivity is the camera spectral sensitivity, we can get the camera responses. Next slide, please. Now we come to the first application, spectral sensitivity estimation. Camera spectral sensitivity is an important factor in digital imaging and color reproduction. It represents the spectral responses of a camera at different wavelengths and can be utilized in a variety of applications, such as multispectral imaging, color constancy, illuminant estimation, and filter design. The standard method to calibrate the spectral sensitivities is to use a monochromator. This method is accurate, but is high cost and time consuming. As a result, various studies have focused on the estimation of camera spectral sensitivities. Next slide, please. Our studies mainly focused on the different color samples for spectral sensitivity estimation, including a reflective color chart, a multi-channel LED device, and a display. We conducted experiments to capture the different color samples by a test camera and implemented different algorithms and evaluated the accuracy in terms of different metrics. It was found that using LED-based color samples could estimate the spectral sensitivities with the highest accuracy. Next slide, please. Next, I will introduce the multispectral imaging. Spectral reflectance is the fingerprint of object color. It represents the ratio of light reflected by a surface color at different wavelengths. For example, if we focus on the visible spectrum from 400 nanometer to 700 nanometer, and sample the wavelength at an interval of 10 nanometer, then the dimensionality of the spectral reflectance is 31. Spectral reflectance is the most fundamental characteristic of an object. To specify its color, only when a spectral match occurs between 2 objects can their colors match under arbitrary illuminant and observer conditions. In a common RGB image, each pixel contains the corresponding RGB values, while multispectral imaging aims to get an image in which each pixel is the spectral reflectance or spectral readings. It has much higher dimensionality than a common RGB image. Next slide, please. The application of multispectral imaging include cultural heritage, remote sensing, color measurement, object identification, etc. For example, in this figure, the left one is an RGB image, the right one is a multispectral image. It can recognize the words that were written in different inks, which is not possible using the common RGB imaging. Next slide, please. Different types of multispectral imaging systems have been proposed in the literature and have been available in the industry. In a filter-based imaging system, a set of optical filters in a filter wheel was placed in front of a monochrome camera. The filters will allow different wavelengths of light to pass through, and the images of a scene are captured by a camera with each of the filters in a sequence in order to get the multispectral image. The filter array multispectral imaging system is based on the extension of filter array from the 3 channels as in Bayer pattern to more than 3 channels, so that a multi-channel image can be obtained. Next slide, please. Next, I will introduce the multispectral imaging system based on a multi-channel LED. This system contains a camera and a multi-channel LED system. The camera can be an RGB camera or a monochrome camera. For example, here we have an LED system with 14 channels. This figure shows their spectrums. It can be seen that they are all independent from each other. We can turn on, turn off, and adjust the luminance of each LED channel. When the LED system is used for multispectral imaging, we can turn on each of the LED channels in a sequence and capture a series of images using the camera, so that we can get 14 images in total. Then the spectral image of the scene is obtained using a spectral reconstruction method. The LED-based multispectral imaging system has the advantage of high speed, high spatial and spectral resolutions, and low cost. But these techniques face the challenges of the light uniformity and the demand of high-intensity LED lights. This LED-based has been widely applied in both academic research and industry. I hope my introduction can help you to have a better understanding on both digital camera imaging and multispectral imaging. That's all. Thank you.
Excellent. Thank you. Thank you. John.
Okay, now Fiona has told us about fidelity. Grace Zhu is going to tell us about making a preferred color. Grace received her PhD from Zhejiang University in optical engineering. Currently, she's a postdoc candidate at Zhejiang University. Her research interests include color appearance models and image processing. For today's presentation, she will introduce the technology designed to achieve preferred color reproduction for mobile devices.
Okay.
Yeah.
Thank you for the introduction. I'm Grace Zhu. And
You're
We
very
cannot hear
quiet.
you.
Grace.
okay. I will
Louder,
introduce
please.
okay.
Yeah.
I will introduce the chapter 2 about picturesque. Okay. From the chapter 1, we have already get a device or an image with high fidelity, but we want more than that because image is a reproduction of the real world. An image with perfect quality could express the satisfaction of beauty to anyone, especially when it recalls an impressive landscape or an unforgettable moment. For example, if we take photos of our friends, we prefer to have a beautiful complexion. So the next stage is how to get a preferred image. And we believe that the key point here is memory color, which is a typical color of an object that an observer acquires frequently and memorize stably through his or her experience. From our previous studies, the image quality could be largely affected by the memory color. Next, please. Next, please.
Yeah, it is there now.
Okay.
You don't.
Based on that, I don't say that. Okay, based on that, we developed a tool to achieve preferred color reproduction. Firstly, we built up a large memory color database and selected objects which were mainly comprised of skin tones, familiar vegetables and fruits, and important scenery objects, for example, summer grass and blue sky. And the selection of memory color was aimed to cover a wide range of hues, including red, green, yellow, blue, magenta, cyan, and so on. So but it was difficult to find natural colors in the cyan region. So artificial objects like Smurf was included. Next, please. After the selection, we built up a rendering database by changing the color of the object. Taking the blue sky as an example, we generated 49 sky images with different colors. Then a psychophysics experiment was conducted. Observer assessed each sky image on the display. The evaluation had a threshold method to judge the memory color in the image. For example, like or dislike. Finally, we got a most preferred skin color center and also the chromatic values and the reflectance curve. Next, please. So on the PMCC chart, each memory color was defined by a name, reflectance curve, and the CIE LAB values. The curve is carefully controlled to simulate the real objects. Next, please. As we all know, Macbeth's color check chart has been regarded as the color standard for many industries, covering photography, imaging, and printing. But it can be found that there are only 5 memory colors in it, so it will be the limitation of the chart. So for PMCC, we got 14 memory colors, including 4 skin tones with different ethnic groups, and also the pork, carrot, orange, banana, green apple, grass, smurf, blue sky, lavender, purple cabbage. And it contains 6 unitary hues to test and define the color gamut, and 6 neutral colors as a grayscale. Next, please. And it can be applied to many industries related to image engineering as test target for assessing the color quality of camera, display, and lighting. For example, to assess the neutrality and do the gray checking by the grayscale. Also to define the color gamut value and unitary hue shift by the unitary colors, and to do the auto white balance as a reference, to be the database to establish the ICC profile, and also to enhance the image quality in the image signal processing. On the following slides, we will give 2 examples to show the specific applications of PMCC. Next, please. The first one is to build up an ICC profile for camera to correct the color of the photos. User can put the chart in the scene and take a photo for the calibration. The color patches of PMCC can be identified automatically. Each color was transformed to RGB values, and a camera profile is applied. Then the output of the camera was calibrated, which means the captured image was enhanced with a better color performance. So the memory color in the images are closer to the preferred memory color. Therefore, we can improve the image quality of the camera with high preference. Next, please. The second application is enhancing the image quality in the image processing. For example, when you are using Photoshop to beautify a portrait photo, it may be found that the original image has a bad complexion. If we extract the error of skin color and calculate the average color, it will be far away from the number 2 patch on PMCC, which is a preferred skin color for Oriental. So refer to the PMCC, we can adjust the skin color of the face and the arms to the preferred skin tone. Consequently, we can get an enhanced image with good complexion. That's all for my part. Now I will give the floor to Merlin.
Thanks, Grace. Okay. So John, next one's Merlin.
Hey, one comment before. I noted in the chat box that if you have any questions for any of these speakers today, please put them in the chat box. We will have some time at the end where the questions will be asked and we will address them. So Merlin Li received his Bachelor of Science degree in Optical Engineering from Zhejiang University. Currently, he is a master's student supervised by Professor Ronnier at Zhejiang University. His research focuses on color appearance under high dynamic range conditions. What does something look like when we're under very bright light? Merlin will focus on the color changes of appearances of objects due to illumination and the application of this phenomena to digital images. Merlin, please take over.
Thank you for the introduction. Today, I will be discussing the evolution and application of color variation, starting from the Munsell color system and the CIE color space, leading up to the two-dimensional color appearance scale. The Munsell color system was developed by Albert Munsell in the early 20th century. Munsell was an artist who was frustrated with the limitation of existing color systems. He believed that a more precise and systematic approach to color representation was needed. To achieve this, Munsell realized that color could be organized in a three-dimensional space, with hue as the horizon axis, value as the vertical axis, and chroma as the depth axis. He began creating a series of color chips using the pigments to represent this space, and worked with his academic and artist peers to refine and improve the system. In 1905, he published his book, A Color Notation, to introduce his system to a wider audience. The picture in the right hand is a demonstration of Munsell color order system. Sorry, left hand. The ring is consistent of hue, red, yellow, green, blue, purple, and its interval color. The value and chroma are collected into a Munsell color page, which is one part of the formal ring. So, if you want to find the color you want, you should first pick a hue from the ring. Then, let the color compare with the color in the Munsell color page. The most related color is the answer Munsell told to you. The Munsell color system provides a more accurate and consistent way to represent color, while it is useful to artists and designers. Its complex notation system can be challenging for some individuals. In the 1970s, the CIE developed the CIE LAB color space. This system used a three-dimensional space to represent color based on its lightness, chroma, and hue. The system consists of a round ball to represent color space, with the axis represents color chroma, the z-axis represents lightness, and the polar angle represents hue. The CIE LAB color space provides a more perspectively uniform color space that actually represents the full range of color perceived able by the human eye. While it is commonly used in color management and scientific research, it's also a complex system that can be difficult to understand and use effectively. Both the Munsell color system and CIE color space has advantage and limitation. While the Munsell color system is used for artists and designers, its complex notation system can be challenging for some individuals. The CIE-LB color space is commonly used in color management and research, but is not a good tool to describe the color change in color space. So we should find the regulation of color change in real life. Next page. In the first figure on this slide, there is an orange chip held on a wooden stick and illuminated by a light source. Two arrows depict the direction of the light, with the green arrow indicating the orange color from the shadow to shade, and the blue arrow indicating the shade color to the self-luminous white in front of the illumination. This orange chip is an example of how different lighting conditions can affect the appearance of color. The second figure on this slide shows the color capture of the orange chip in the CIE-LB color space. This scatter diagram is plotted on the horizontal axis of chroma and the vertical axis of lightness. The green arrow corresponding to the arrow in the left picture. And we can see from the figure that the color changes as lightness and the chroma increase together. On the other hand, the blue arrows indicate that the color change as lightness increase, while chroma decrease. This illustrates that color changes are not simply a matter of color change in lightness or chroma alone, but rather the complex interaction of both factors. The third figure on this slide is the description of lightness and the chroma in the dyeing industry. The double-headed arrow in the middle represents different words used to describe color change in the 1960s dye and the textile industry. For example, brighter represents lightness increase in the dye industry, and cleaner is used in the textile industry as the same meaning. While dirtier and duller represent their corresponding decrease. Similarly, stronger and deeper indicate the increased chroma, while weaker and whiter indicate their decrease. However, color change involves both lightness and chroma. Burns rotated this color change descriptors by 45 degrees to better fit the description of color, leading to the idea of vividness and depth. Next page. This slide shows a two-frame animation. Please, okay. The first frame is a photo valley illuminated by sunlight. It has been optimized by enhancing the chroma of the image. As you can see, the colors are more vivid and intense, giving the image a cheeky, heavy feel reminiscent of oil painting. However, while the image may be visually striking, the color enhancement can also make it look artificial and unrealistic. On the other hand, the second frame, the last page, please. On the other hand, the second frame of the image has been optimized using the vividness idea. As opposed to enhancing chroma, vividness takes into account the balance between lightness and chroma in order to create more natural, pleasing colors. It looks more true to life and less exaggerative than the color-enhanced version. This slide is a virtual comparison of the two images from the last slide. We can see that the image on the left, which is the image on the right, which is optimized using the vividness approach, has a brighter and more impactful look overall. The sunlight in the image appears even brighter and more intense, giving the viewer a stronger sense of being in the moment. The use of vividness optimization is gaining more attention in the field of display technology, and the company like Samsung are already incorporating it their products. By utilizing this approach, we can create more visually appealing and natural-looking images that are better suited to the way our eyes perceive color. Next page. In addition to enhancing display effects, vividness and depth can also be used to explore color patterns. In this slide, we have a standard memory color image of blue sky, white cloud, and green grass on the left. While on the right, we have the color distribution of blue sky and the white cloud, and the green grass in the CIE-LB color space. Looking at the blue sky and the white cloud, we can see that the color distribution are not uniform and vary in direction, which could be used to recognize objects. Additionally, we can determine the quality of the light source or image by the degree of color dispersion. Moreover, both the blue sky and the white clouds are self-luminous color, and their variation also follows the depth direction. This raises the question of whether all self-luminous color variation follow the depth direction. Moving on to the green grass, as a non-self-luminous object color, the color variation follows the vividness direction. Therefore, can we optimize color by using the varying direction of different color in memory colors? There are all potential future application of vividness and depth in color exploration. Next page. This slide presents a different perspective on color analysis. On the left, there is an orange being illuminated by natural light. By plotting all the colors of the orange on the LC plane, we can observe both vividness and depth direction in the color distribution. This leads us to consider the possibility of both object color and self-luminous color pattern existing on the orange. By using the 2D scale approach, we can expand our understanding of color variation and discover new ways to apply color for cognitive recognition. This method can help us identify new insight into the properties of color and enhance our ability to analyze and manipulate color in various fields such as art, design, and technology. That's all my presentation. Thank you.
Thanks,
Well, thank you,
Merlin. So I like to use this, opportunity to make a conclusions. Okay. So color science is fun. All the audience, right, are associated with color. We look at the color day in, day out, right? It's a wonderful, experience. Okay. We are colorful, we are always positive. Okay. So tremendous, pleasure to work with students over the years. Okay. And color science, basically still the same, 30, 40 years ago. But now, right, we apply it to the much wider range. Okay. So we mentioned about the well-being. We also mentioned about the color design. We don't have the opportunity, right, to present our results. But we've been very much engaged with the mobile imaging these days. So Fiona talked about the fidelity, and previously, right, or now very much in the XYZ, the color reproduction, we call colorimetric. But now, right, we move into spectral reproduction. I think the era has come because we have technology to do it, right? And the preferred color reproduction, right, is we always like, the image, right, is have a full fidelity, true ground truth, right? We may not like it, so we needed to have tool to achieve the preferred color reproductions. Okay, so we presented a technique we call the PMCC, the preferred memory color chart. to do the preferred color reproduction. And finally, right, is the, the lightness, chroma, and the hue. These are the what we call the three, individual dimensional scales, or single dimensional scales in the 3D space. But you will find, right, is in the real world, and we don't use that, okay? When the light impact to any objects, it's an interaction between the lightness and the chroma and even hues, right? So color scales, right, we need a natural scale to reflect the impact of lighting on objects, okay? So I think I conclude, right, our presentations, and thanks for your attention, right? Thank you.
All very interesting today. A round of applause for everybody here.
Thank you.
Jean, did you want to go through questions here?
Yes, we have some questions. The first one is for Dr. Luo. You mentioned cams in your initial presentation. As an artist, I intensely use the forward and reverse transforms outlined in your CAM 16 paper. I hope you know which paper that is. Using the color science package written in Python founded by JetBrains. The I guess it's NumPy, N-U-M-P-Y, based array workflow is vectorized and optimal for image processing. In 2020, you wrote your paper on Zcam. I'm excited to work with it. However, it doesn't appear that any publicly available packages are working with it, despite its superior performance. Perhaps my Googling skills are poor. Are there any available tools that implement it so that I can use it?
Right.
So the question is are there any tools that he can use for the Zcam?
Yeah, right, is I think you wrote, to me, and you address this, right, is, we developed the model, and I believe we have in some work the examples there, but we don't have a, exemplar program for the use, for the usage, right? It is always in my mind, right? Is in our website we put the database and together with the program coding there, to assist the users, right? I apologize, right, for this, but we will do it, okay? Every time.
So say, Nadar, you have a commitment from Dr. Luo that he will publicize that for you. Check his website.
Right, is the students come and go, right? Is the way they should do this, right? Is the but I forget, right? Is the to ask them to do it, okay? But I will do it. Zcam, right? Is the considering what is the best color appearance model available, right? Is the CCAM 16, right? Without any doubt, in terms of, right, is the uniformity of the colors, all this, right? It's fine. But the hue linearity, right, is poor. Okay, I won't say it's poor, only poor in the blue region. Okay, but what is the and people familiar with IPT, and the type of the spacing, they are good in hue linearity, but they are poor in uniformity. So what is saying, right? There's two criteria, right? Which space, right, can do that? Zcam and the JZAZBZ. Okay, but but they are too new. We are developing the color standard, and it takes ages, right, to develop standard. Once it's been published, the new standards coming, but the research, right, the new models also, right, come out. So and we need to be very cautious. Okay, we're saying what is the best model available now. We will say CCAM 16, right? And Zcam and the JZAZBZ, they are coming. They're not replacing. They are research models. They should be investigated, and we should deliver the code for people to use these models. Okay, thank you.
So, Grace, is the PMCC available commercially? It sounds like a product than the Munsell color checker.
Okay.
Yes, it is in production, and it is tested by several labs, and also the industries.
So we are looking at the end of April, and the 1,000, cards that will be available, right?
Can you tell us more about your color research and how it impacts the well-being of different groups of people? You mentioned that as one of the factors in cell phone technology.
Okay. And we're looking at the two aspects, right? It's one we call the visual comfort, right? So visual comfort is defined, right, is by the visibility of the words on the background. Okay. So we look at the very simple scenario, the white paper, and the black words, but they have different contrast. Okay. So the first one is we call the visual comfort, which is defined, right, is we now have a psychometric scale to describe the visual comfort. The visual comfort is described as, right, is the readability, and also, right, it's not dazzling, not too bright. When you read in the dark, it's a very bright background, you feel uncomfortable, right? So that's number one, right? Is we are developing a scale we call visual, and comfort. So any display in the future, right? We like to have a visual comfort assessment. So we give them a numbers to indicate, right, is displays, quality, right? The second one is considering, right, is the colored combination, colored words and the colored background. Third one, right, is the circadian. Circadian, right, is we all read in using mobile phone in the late night and early morning. So if you don't, right, is get the color right, so that your circadian rhythm will be affected. So you will not, it will affect your work performance, and it will affect your, sleeping quality. Okay. And finally, right, is we consider the color blind and the color, deficiency observers, right? So they have about, right, 8.5% in the world. They are the minority, and we should look after them. Okay. And our system, right, is also consider different age groups. Okay. So I mentioned, right, a number of the, issues we are doing research on that. Okay. So all this, right, are considering the well-being, and how we protect our eyes when we apply the, using the mobile devices.
Okay, so thank you very much for that. Also, I'm an artist as well, and so I was wondering, you have the lightness and chroma scales. Is there research going on in the dimension of hue?
We have done a lot of, right, is psychophysical experiments, right, to scale colors, and considering with the lightness, chroma, and the hue, right, hue is the most consistent. It's very consistent across all different ethnic groups as well. Okay, so right, is the hue, right, is there are two kinds of hue. One is, right, is what we call the, right, is the 4 unitary hue: red, green, and yellow, and blue. There are 2 pairs of the complementary colors. Yeah. So that is based on the, right, is the NCS the system to describe the color appearance, and Munsell, right, is using the red, yellow, green, blue, and the purple, right, because they considering the color difference. There is a paper, right, is coming from the color research and application by Mark Fairchild. Just particularly on the hue, it will come out very, very soon. And so I recommend, right, people to read that. There are 2 kinds of the hue scales. As far as you clearly define it, this is for color difference purpose. That is for color appearance purpose, right? And then, right, people can scale that very accurately. But people are struggling to scale the chroma scale. It's very difficult. right? So the vividness, why is difficult? Because the vividness and the depths, right? They are frequently used. That is what we found, okay?
In fact, since you mentioned chroma, there's a question that, have you found that the C-Lab chroma is confusing, non-intuitive? Is there a vividness metric derived from L star, A star, B star?
Yeah, you know, the first one, right, is the, I'm chaired a CIETC, you know, technical committee. Our goal, right, is to develop the vividness and the depth, the scales. It's from the LAB or secant, okay? So the model will come out. But for the time being, right, it's the one that proposed by Roy Burns, right, is the in that paper, right, is the given by Merlin. You know, Roy is the paper in the color research and application. That is the right good one to be referred to, right? So the question is, right, do you have a model? Yes, it's been published in the color research and application, and Merlin's talk, right, using that as the examples. Okay.
All right, so we've reached the top of the hour. So Luann or John, do you have any closing remarks?
I was just thinking, just quickly, maybe we'd be able to provide a link to Merlin's paper afterwards to for everyone. And we're going to actually have the recording available, but that'd be good to have the links to the research.
Yeah. So you are welcome. We have the website there. You can access to our website. All our papers are there, our research resources, and our staff and the students. Yeah.
I thought this was fascinating today. So I greatly appreciate having you all present to us today.
It's our pleasure as well, you know, and we really enjoyed it. Thank you.
Okay, we will have Fluorescent Fridays again. Luann, when is it? Do we have a plan for the next one?
Yes, it's going to be in April, so stay tuned. I think it's the third week of April. We'll let you know, and it'll be presentations from RIT.
Okay,
Wonderful.
cool.
Yeah, we look forward to it. Okay.
Well, thank you for staying up late and presenting to us.
Thank you. Try to say bye-bye. Yeah.
Bye.
Bye, everyone.